Okay, I tossed a chalk. Somebody caught it. Good catch. Okay? Asked people how long it took to get there. People thought it took 6 minutes. Well, that wasn't a good estimate. So I tossed it, and I counted 1, 2, 3, 4, 1, 2, 3, 4, 1. That's about a second, counting quarter seconds, right? And it was 1, 2, 3, 4, but not quite the 1. Okay? So I'm estimating it took 0.938 seconds. But we'll just say 0.9. Excuse me. I get choked up over projectiles too. Okay. So chalk traveled 4.6 meters in the horizontal direction. In 0.9 seconds. Now, I released the chalk from this height. Well, you can't see it on the video, but you see where my arm is, so you can extend down here and see it was just a little bit lower than this, right? Okay. Now you were sitting when you caught it, so you're down here and you caught it up about here. Now that's about here is where they say so. So obviously you caught it at a point 0.6 of a meter higher than I threw it. So the net vertical displacement net vertical displacement was 0.6 of a meter. So if you try to draw the path is like from here to a point here a little higher, and there's some kind of an arc here. Okay? How far did the chalk travel? Well, the chalk didn't travel along a straight line. Okay? But there's your straight line displacement factor. It has components. We'll say we'll let the I direction be from here to there, okay? We'll let the J direction be upward. We could call that the K direction equally well, but since the entire motion is in a single plane, and a vertical plane in this case, we don't need K. But if you like K better, you can use it. It works equally well. So you got 4.6 meters I, 0.6 meters times J. So this vector that I'll color code in orange. Okay, the displacement factor is 4.6 meters times I plus 0.6 meters times J. Magnitude is the square root of .6 squared plus 0.6 squared meters. Okay? And I don't think that's, you can check me out, my intuition is that's only less than 1/7 of that. So 1/24 might be 4.8 meters. My intuition says it's more like 4.7. But quick calculation I just did in my head said 4.8, and I'm not going to double check the calculation, okay? Probably around 4.7, but we'll see. Okay. Now that's not particularly important for what we're going to do, but we want to put this in context. The actual distance it traveled is greater than the magnitude because it's an arc. Shortest distance between 2 points is a straight line. That's not what the thing traveled. It traveled an arc. The arc had a high point, and the arc is, turns out, a parabola. We can prove that in a minute, but I'll just say it. Now, I say this is a parabolic arc. If we did careful measurements with the best instruments we can come up with in this lab, we could not tell that it is not a parabolic arc. But I know it's not quite a parabolic arc because there's air resistance involved that affects the equations of motion in the vertical and horizontal direction a tiny bit, okay? But it's only a tiny bit for something of this density and something that's traveling about 10 miles an hour, okay? Now that wasn't my 104 mile an hour fastball, okay? I think even they would have trouble catching it if I threw my 110 mile an hour fastball. Okay, well, you know, I got a great nephew, just turned 12. One of the smartest kids I've ever seen, too. Mom's an obstetrician. She's my niece, but she's very smart. I have a little trouble riding with my wrist. It's because summer before last, he was throwing his fastball at 59 miles an hour. And I was hitting it, okay? And I was hitting it. I couldn't control where it went, but I pretty much hit it every time. But I have to swing a heavy bat because I tend to get ahead of things and into my wrist, okay? And it got pretty much better by Christmas, but it's flared up again. Now that doesn't have a whole lot to do with this. He's now throwing close to 70 miles an hour. Just turned 12. And they're kids in his, he's on a travel team. They're kids that have slightly faster fastballs. They're mostly older than he is, not that much older. Still pretty good fastball. Okay. And I'm pretty sure I never threw a fastball faster than he's throwing it right now. Had a good arm for throwing a football, but I couldn't throw a baseball. I don't know how that is. Okay, anyhow. So I'll give you some statistics and let you figure out how fast I could throw a football later after we do this. Okay? Because I know how far I can throw it. Nothing to brag about, but pretty good throw. Okay. So I'll leave you in suspense over that one. Okay, distance traveled. I'll say this. One reason I could throw a football pretty far is I used to throw it with Fat Boy. And Fat Boy would stand at the boundary of his property. I'd take off running. 10, 15 minutes later, I'd be about 50 yards downfield. He'd throw the ball. I'd run like crazy, and about 10 minutes later, I'd catch it just short of the far property line on his neighbor's property, and those are 40-yard lots. So how far was he throwing the ball? Darn near 80 yards. Okay? He walked on at Ohio State, not quick enough to be a quarterback. He was also just the best athlete I knew. He was doing okay at linebacker, and then he hurt his shoulder, so that went downhill. Okay, so throwing the football with him, I started throwing it fairly far, but nowhere near what he did. Kind of interesting the way that works out. Okay, so my best throw is nothing to brag about. It's not bad. My shoulder's destroyed now. I couldn't throw a football from here to there. Can't cock the arm. And the mechanics of that's kind of interesting too. When your humerus locks into your scapula, you lose your ability to throw anything. And it's no loss to humanity. It wasn't accurate. It didn't have to be accurate. Taplock could go anywhere and catch it. Okay. I could just talk about projectiles. Just that, that was spontaneous. I wasn't planning to talk about that. Okay. So you've got this parabolic arc. And what we really want to focus on is how this moves in the horizontal direction and how it moves in the vertical direction. Well, in the horizontal direction, it just goes from here to here. Long, straight. You can say, okay, we'll just do a straight line path from here to here. Okay? At 4.6 meters divided by 0.9 seconds. A little over 5 meters per second. Okay? And meter per second is about 2.3 miles an hour, I think. Between 2.2 and 2.3. That's about 11.5 miles an hour, actually. Faster than I thought. I didn't think I could do that. Okay? What did it do vertically? Oh, vertically, it went up, and then it came back down to this height, right? So vertically, it started off at, we could call this y equals 0 if we wanted to. Y equals 0 doesn't have to be the floor. Could be the center of the earth, but then the numbers would get big. Okay? So we can put y equals 0 there. That's a convenient place for y to equal 0. So your change in y is 0.6 meters. Now there are 2 points at which the y coordinate was 6 meters. There's 0.6 meters. There's this point and this point, right? Now remember what we did last time, pull ball up and down the incline. And we figured out when the pool ball might have been 10 inches from the starting point, right? 10 inches from the starting point at one time going forward and at another time coming backward. And we got a quadratic equation for the position, which is easy to solve if you remember the quadratic formula. If you don't, get it straight and never forget it again, okay? And by the time this course is done with you, you'll probably be unable to ever forget it again, because you're going to use it a fair amount. Okay, so what can we do? Well, we can say this. We can say that x of t equals we could say x naught plus v naught t plus 1/2 at squared from here to there. What do you think the acceleration is in that direction? Give you a hint. What forces are acting on the chalk as it travels? from here to there?
Gravity.
Gravity. Any others?
Air. Force in which you threw it.
Sorry.
The force you tossed it with.
Force of my throw, you mean?
Yes.
Well, that's not acting. After it really leaves my, that's a good thought, because that's a common thought, and I'm glad you mentioned that. But after the thing has left my hand, the force of my throw is gone. The force of my throw gets it up to speed, right? And then that force no longer acts. Okay? So there's nothing in that direction for my hand that speeds it up or slows it down. So if there are no forces in that direction, then the thing travels at constant speed in the horizontal direction. In the vertical direction, there's gravity, as you said. Okay, that affects the vertical motion, but it doesn't affect the horizontal motion. Now there is a little bit of air resistance, and that does tend to slow it down a little. Well, it does slow it down a little bit, okay? But that chalk is fairly dense and it's not moving that fast. You don't get that much air resistance at 10 miles an hour. Probably not enough that, if we pump all the air out of this room and I toss it over there, well, we better keep the air out for a very short time or we'll die. We'll probably end up hospitalized anyway, okay? You got, maybe 20 or 30 seconds if you get into a vacuum. And it's going to be really uncomfortable, you're going to swell up. It's going to be, you don't want it. Okay, but if it was a vacuum, then that chalk would get there just a little sooner, okay? So if we compare the motion side by side, like we did with the two pool balls over there, okay? Where one pool ball on one track, because of the geometry of the track and stuff, was behind the other one by about 10 inches, okay? I don't think that the piece of chalk in the room, in air, would be more than a few millimeters, if that, behind the chalk in a vacuum, okay? And in a vacuum, of course, you'd have no air resistance. Have you ever seen the demonstration where they drop a feather, which floats down pretty slowly, drop it in air, and then they take all the air out of a tube, and they've got a little release in there, and it releases a feather, and it drops just as fast as a cannonball would. That's worth looking up. Just Google feather in vacuum. You'll probably find it. It's a pretty well-known demonstration. It might be there in the open math. I mean, in the my lab. Okay. We've got some really good demonstrations in my lab. Okay. Excellent demonstrations in your assignment for Monday. And some of the first things you do is you look at them. Okay? And you try to puzzle out what's going on. Gives you a better feel for this kind of motion. Just like thinking about that chalk can give you a pretty good feel for some things. Thinking about what I'm saying here. Thinking about a football pass. Okay? I cocked my left arm, but I can't throw anything. Okay. Okay. So anyhow, bottom line is the acceleration in the x direction, and of course your book puts an x subscript on these quantities, right? And that wasn't particularly important before when it was all in one dimension. It's kind of always the x-axis. Okay, but now that we're getting into an x and a y, or if you want an x and a z, you got to have to put x and y subscripts on these quantities. Okay. So now I can say that this acceleration is 0 at first approximation, and we're not going to deal right now with air resistance. That requires differential equations beyond the scope of even a calculus course, okay? It's the end of second year calculus. And even at that, the actual equations can't be solved, except numerically. Now you make certain assumptions and you get equations that can be solved, and they're pretty close. Okay, anyhow. V naught x, well, that's whatever the velocity was in the x direction when I released the chalk. X naught, we might as well call it 0. Okay. X of t equals V0x times t. And what information do we have? Well, we have x of 0.9 seconds equals V naught x times 0.9 seconds. X at 0.9 seconds, that's not multiplication, that's a function notation. X at 0.9 seconds, we know to be 4.6 meters. We got that from my incredibly calibrated pace. Okay? And my unfathomable ability to estimate decimal fractions, right? Well, actually, it's 4.6 meters, probably plus or minus 0.3 meters. Okay, I think it's pretty close to a meter. I'm not sure about that 0.6, okay? I mean, each step is pretty close to a meter. Okay, so anyhow, you got 4.6 meters equals V0x times 0.9 seconds. And this is, I'm going into a lot of detail here, but that's about 5.1 meters per second. And that's going to be constant during the phase where acceleration is uniform. Acceleration is uniform from the instant the chalk leaves my hand to the instant it touches your fingers over there, right? Or palm, whatever part of your. I used to be pretty good at catching candy in my mouth. People throw it from miles away. Okay? But I noticed just because of the mask, you chose not to catch the chalk in your mouth. And I'm kind of glad you did, because I didn't want a damn piece of chalk coming back at me. Okay. Okay, so, make sense? You want to lock this in. You never want to be confused about what happens in the x direction with a projectile. It moves at constant velocity. And you're going to see that you're going to see some good demonstrations that even establish that much better than you can from me just telling you about it. Okay? Okay. Now, what about y of t? It's equal to y naught plus v naught yt plus 1/2 ay t squared. Well, ay is the acceleration of gravity. I'm going to call that negative g. We use little g for the magnitude of the acceleration of gravity. And in open math, you're going to want to use 9.8 meters per second squared, maybe even 9.81 meters per second squared, because they're picky about that, which I think is unnecessary. Okay, 9.8 is pretty close to 10, isn't it? It's only about 2% less than 10. So you calculate using 10 meters per second squared, okay? And then just take 2% off. Comes out really close to 9.81, okay? So just quick and dirty calculation, if you just want to do a calculation in your head, real easy to use 10. And that changes this term by 2%. So take 2% off. And that's easy to do 2%. You just double your result and put the decimal in the right place and make sure your intuition's right. Okay, well, that's handy. But anyhow, I'm saying G then is approximately negative 10 meters per second squared, because G is approximately 10 meters per second squared. And we can measure that. I could drop a steel ball from 1 meter, and using my incredible ability to estimate time, come out with the fact that it's between 0.43 and 0.44 seconds. Okay? Now there are other things we can do. We can hook a microphone into one of our fancy interfaces and release the thing using something that makes sound, like hold it on a piece of steel and hit the piece of steel with a hammer, goes out from under and the thing falls, and then it makes noise when it hits the floor, right? And then you get the output, just a simple graph. It's going to have a spike here and a spike there. Okay? So you're going to be able to tell pretty accurately, because this thing will measure sound down to a resolution better than a 10,000th of a second, close to 100,000th. Okay? And your only problem in reading this thing is figuring out when the middle of that spike is. And then you get a very accurate determination. So accurate that you have to worry about if your microphone is a little further from where the thing lands than from the sound of the landing and the sound of the release. You got to correct for that on the speed of sound. Okay? Because 1 foot is 1,000th of a second. You're measuring time on the order of 100,000th of a second. Okay? So if you're a couple feet further, that's a couple thousandths of a second. So my point is, in this lab, using sound, we can pretty accurately measure the acceleration of gravity. Okay, we can see how long it takes to fall 1 meter. We can see how long it takes to fall 2 meters. If we get the same result for the acceleration of gravity, it's pretty good confirmation that it's the same no matter how far it drops. Okay? Then technical issues. If we want to go much over 2 meters, it gets a little harder to set it up, but it could be done. Okay, so we can measure this. That's the point. This can be measured. And we would come out pretty close. So close, maybe, that we can account for the fact that at 2,000 feet elevation, and with the geology around us, the acceleration of gravity is somewhat less than 9.81 meters per second squared, which is a standard value at sea level. It varies from one point on the Earth to the other, with altitude, also with the density of matter beneath your feet. Okay? If some fool had buried a 1 kilometer sphere of gold just beneath us, it would really screw up our measurements of gravity. Okay, the gold is much denser, and it's close enough that the gravitational attraction would significantly affect the acceleration of gravity. If I tried to throw a football in the vicinity of that thing, if I was accurate, I'd end up a little less accurate. I'm not accurate, so I never was. So, I wouldn't be able to tell the difference. But a pro quarterback probably could. Okay. So yeah, I keep underthrowing that guy by an inch. What's wrong here? I know what I'm doing. Well, and then he'd adjust for it, and then he'd go play the game, and he'd be overthrown by an inch. That's terrible. Okay, well, there's your acceleration of gravity in the y direction, right? Well, if you assume y naught equals 0, and I wrote this out quickly without thinking about information I'd already supplied. Okay, that would actually be like 4.9 meters per second squared if you use the 9.8, which you better use when you do the MyLab, okay? But right there's your equation for y. Okay? The graph of y versus t, well, this is a quadratic equation with a negative coefficient of t squared, or a quadratic function. Y is a quadratic function of t, okay? With a negative value of t squared, meaning that y versus t has a graph that looks like this. But this is y naught. Now that's in general. In this specific case, we assign y naught to be 0. We assign the origin of our coordinate system to be this point. Then the y motion as a function of t can be represented by a parabola that's got an origin at that passes through the origin of the y versus t. Now be careful, this isn't the arc. The arc is in y versus x, right? And this is a little more abstract. This is y versus t. You can't see this. You can watch this arc, okay? That's not something you can physically see, though, but it's a representation. Well, what you know then is that y starts here and ends at 0.6 meters, right? So if this is 0.6 meters, then the catch occurs at this point on the graph of y versus t, right?